Next, we have Jinshan Xiong. How'd I do? I'm practicing. Better? All right, right on. Jinshan is based in Dublin, California. He's been working on the Lustre project for 10 years through various companies and is currently senior Lustre engineer at Intel. Among his many contributions to the Lustre codebase is the OpenSFS-funded client I/O simplification. So, Lustre I/O performance on ZFS. Thanks, Jinshan.
Thank you. So today I'm going to present the latest ZFS I/O performance. Okay, so this is the agenda for today. So first of all, I'm going to briefly introduce the architecture of Lustre on ZFS and the reason why do we choose ZFS as a Lustre backend storage. And then I'm going to review latest ZFS I/O performance on Lustre. And then I'm going to follow up the presentation SDSC, that is San Diego Supercomputer Center, did last year about ZFS, tickets and and new work. And at the end of the presentation, I'm going to propose some new work we're going to do for to boost ZFS I/O performance further. So why do we choose ZFS as Lustre back storage? It's because all of these good things. ZFS can deliver really good I/O write performance because writing ZFS are always sequential on disk. And it is also always on disk persistent, which means there's no need for the FS check. And it has several really great built-in features, for example, like disk management, RAID-Z mirror, etc. And also it has built-in block checksum and built-in data scrub support. So metadata is also duplicated in ZFS by default for redundancy. So therefore, you may be able to lose several disks, but still your file system is still accessible. Okay, so we benchmark the latest ZFS I/O performance with this hardware. So we have 20 client nodes and 2 MDS server and 2 OSS servers. So on each OSS server, it has 28 CPU cores, and the 2 OSS servers share 116 disks. The client has 20 cores with 64 megabyte memory. So this is the OBD filter performance result. So actually, as you can see, ZFS is delivering really good write performance. And the red line on the right side is the theoretical maximum throughput. So as you can see, it's really close to deliver the raw throughput disk performance. So we use last community release 2.8 and ZFS 0.6492 because of an existing issue. So I'm going to talk about this more later. So the write performance can be up to 13 gigabytes per second. That means, thinking about the theoretical maximum write performance is about 15 gigabytes per second. So yeah, it's really great. But read performance is not as good as write, and I'm going to give an explanation later. Okay, so this is the ZFS I/O performance, from Lustre clients, and we have 20 clients and 10 OSTs, and so there's 110 disks in total, and one OST has 9+2 ready Z2. So therefore, 90 disks can deliver about 11 gigabytes per second on average. So this is really great. So we use 1 megabyte block size and 4 KB circular size. The reason we choose ZFS 0664 is due to LU7404, and that is a upstream change made by OpenSFS, and caused some performance issue. Okay, so why ZFS deliver worse reader performance? This is because the way ZFS is implemented. So in ZFS, there's no file-aware block allocation, which means blocks written sequentially on file level will be discontiguous on disk, and actually it may spread around the whole pool. And we have a lot of discussion like this on Jira tickets. Therefore, when read them back, it will produce a lot of disk seeks, to locate the data block. So this is why ZFS read is usually worse than write. And we're going to, so actually big block size would mitigate this problem, because each block on disk, will become larger. So you can take a look at the diagram. So for example, block I and block I+1, both from object X, though on the file level, they are written sequentially, but due to, because they belong to different transaction group, there may be some gaps in between. Okay, so next I'm going to review some tickets from SDSC's presentation last year. As you can see, all of the patches mentioned in the SDSC's slide have been landed into 2.8. But there are new tickets coming up, and LU7404, actually this is a really important one. And we identified that the commit to reduce lock contention in arc buffer caused this problem. And we are working with upstream developers on this. So this is why we use ZFS 0642 in 2.8 release. So, we drive the disk storage and ZFS really hard. So though we choose this release for ZFS, it doesn't mean the other releases are bad. So actually, as far as I know, there are some customers who is using 2.8 with latest ZFS release, and they are really happy about the performance and stability. So we are doing a really serious job on quality control. Okay, so in the SDSC's presentation last year, SDSC expected to use AVX2 to compute ZFS RAID Z and Fletcher 4. So these all respond to the request. So we contributed Fletcher 4 with LVX instructions to the ZFS community, and the patch will be, I guess, will be merged in ZFS 070, yeah, if I remember it correctly. And the work about vectorized RAID Z parity is done by a third party, and the ZFS developer, his name is Gvozden. Sorry if I spelled it wrong. He's going to present his excellent work this afternoon. Okay, so I'm going to make some proposal, to boost ZFS I/O performance better. So these three new features are in progress at Intel for ZFS. So large block size and parity decrossed rate and a separate MD allocation class. So we are going to learn them into upstream ZFS on Linux project. And on the Lustre side, we are expecting it should be available around 2.11 community release. Okay, so for the ZFS 16 megabyte block size, so we are proposing to enable 16 megabyte block size for ZFS, and Lustre is also going to be changed to support 16 megabyte RPC. Therefore, we can ensure end-to-end 16 megabyte I/O size. There are some challenges with ZFS memory management. So right now, ZFS use vmalloc-based slabs to manage large arc data buffer. The problem we have seen is that as the time goes by, ZFS cannot allocate memory space from vmalloc anymore due to memory fragmentation. In order to fix this problem, so we have to use scatter page list to store arc data. And also, there's another work in progress at Delphix. It is a complex arc, which may help the memory issue a little bit if your data is compressible. So after 16 megabyte block size is enabled, so we have to support dynamic blocks on OSD ZFS. Yeah, because otherwise there will be way too many read, modify, write for small files, and that will kill performance. So there are two ways to set block size in ZFS on the OSD side. So either application can do this via a dedicated API, or OSD ZFS can choose block size by I/O pattern. So why do we need large block size? So consider a 8+2 RAID Z, ZFS RAID Z again. So for 1 megabyte block size, so every disk drive will store about 128 kilobyte data. So this is kind of a small I/O, right? So in modern disk, you should expect 1 megabyte disk I/O to each individual disk to maximize the performance. So with 16 megabyte block size, we can guarantee 2 megabyte data to each individual disk. Therefore, it can deliver better read performance. Yeah, because your disk I/O is way larger than before. So another work we propose is ZFS D-rate. So why do we need ZFS D-rate? So with ZFS RAID-Z devices, a problem usually seen is that RAID-Z device can deliver good performance when every disk is in good state or in good state. But once a disk in a group fails, the I/O performance will be affected significantly. So this is because the rebuilding bandwidth is limited by a single spare disk. So with ZFS D-rate, the spare blocks can be distributed to all disks. You can take a look at the diagram on the right side. So with D-rate, so there will be so we basically shuffle the disk index by the particular permutation. And for each permutation group, the first permutation is randomly generated. And then we are going to develop the following permutation by shifting disk by one at each time. So with ZFS D-rate, we can see reasonable throughput in degraded mode. Yeah, because we only lost 1 over n disk bandwidth, and n is the total disk in the D-rate. So another work is going on at Intel is to separate MD allocation class. So comparing to the data in ZFS, metadata are usually tiny but more fundamental. Yeah, because you need metadata to locate your data in ZFS. So loading metadata faster is really important to ZFS. It will result in lots of benefits. So we are proposing to have a dedicated top VDEV to store metadata. And this VDEV should be built on faster storage like SSD and NVRAM. And we can also mirror it for redundancy. So in my personal opinion, this is a better use of SSD than L2ARC. Okay, so why do we need this feature? So as I said, loading metadata faster is really important to boost I/O performance, and because it has low read latency, so which means you can load your metadata from SSDs or NVRAM really fast, and also it can improve the scribe or serial performance. It can shorten the time of rebuild. So consider a 8+2 RAID-Z device again. So metadata block size usually varies from half K to 16 kilobytes in ZFS. So for a typical indirect block, which is 16 kilobyte, 8 disks will store 2 kilobytes on each, and this is really bad, very tiny, small I/O, and it will hurt, the overall performance. Yeah, that's it.
questions?
Can you speak to what might happen if you lose the metadata VDEV? What will happen to that pool?
So first of all, you have to define lose. So how can you lose, every disk in the top VDEV?
I guess I just see a different level of, potentially a different level of redundancy in your metadata VDEV than you have in the rest of the pool or in the rest of the VDEV.
Yeah, so
maybe mirrored metadata
yeah.
VDEV versus a RAID Z2 for the rest of the pool.
Yeah, that is possible. Yeah, so in that case, you have to, define some policy to access your metadata, right? Definitely you don't want to access your metadata when your, mirrored metadata in SSD are still available, right? Do I answer your question?
Yeah, it is. I just was concerned. Suppose you lost the connection to your SSDs, even an entire mirror. You still have the rest of the data in what might be a pool that could survive more loss of more drives than metadata.
Yeah, so actually, yeah, this is a good idea. I mean, yeah, some kind of a tiered storage, right? So you store the metadata on faster storage, and you have a backup in the RAID Z pool. And usually, from our data, usually only 2 or 5% of disk space are used to store metadata, which means, so for example, you can have 1 terabyte SSD, and to manage, so for example, 50 terabyte RAID Z pool, and you can definitely make backup, into RAID Z pools.
Thank you.
Yeah.
It's also worth mentioning that, and you had mentioned at the beginning, that at ZFS, the metadata is already mirrored. So in addition to having a mirrored VDEV, I should say it's replicated, right? So you would have, at minimum, for all of the metadata in ZFS, you have 4 copies. And for the high-level metadata, you'll have 6 copies. And so you would probably, if you're concerned of double, SSD failure, I mean, you would probably have at least 3 separate metadata VDEVs, for getting 1 copy on each of those, right?
Okay, thank you.